Near an equilibrium point of a nonlinear system, the local behavior is approximated by the Jacobian matrix of partial derivatives evaluated at that point. Here is our system. The derivative of x1 with respect to time equals x2. The derivative of x2 with respect to time equals negative x1 plus x1 cubed. To find the equilibrium points, we set both derivatives equal to 0. From the first equation, x2 must equal 0. Substituting into the second equation gives negative x1 plus x1 cubed equals 0. Factoring out x1 gives x1 times the quantity x1 squared minus 1 equals 0. This gives 3 equilibrium points. The first is at x1 equals 0. The second is at x1 equals 1. The third is at x1 equals negative 1. In each case, x2 equals 0. Now we build the Jacobian matrix. The top row comes from the first equation, giving 0 and 1. The bottom row comes from the second equation, giving negative 1 plus 3x1 squared and 0. We evaluate this Jacobian at the origin, where x1 equals 0. This simplifies the bottom left entry to negative 1. So the Jacobian at the origin is the matrix, with rows 0, 1, and negative 1, 0. To find the eigenvalues, we solve the characteristic equation lambda squared plus 1 equals 0. This gives eigenvalues of plus I and minus I. These are purely imaginary, which means the linear approximation alone cannot tell us whether the origin is a center or a spiral. To resolve this, we build a conserved energy-like quantity. Let capital H equal 1/2 x2 squared plus 1/2 x1 squared minus 1/4 x1 to the fourth. We check this is conserved by differentiating capital H with respect to time. Using the chain rule, this gives x2 times the derivative of x2 plus x1 times the derivative of x1 minus x1 cubed times the derivative of x1. Substituting our original equations and simplifying, every term cancels, leaving exactly 0. Since capital H stays exactly constant along every trajectory, the origin really is a center. This confirms the inconclusive linear case without needing to guess.